record, yeah, and share the screen again. And we're back in business. Yeah, okay, perfect. Quick comment on the example I ran for the lecture. I lost the graph. It's right here. Is it? Yeah. Okay. So you see that that's the model that we saw before. You see that for survival and in the two sites, the mixing is good, everything goes well, and the autocorrelation doesn't seem to be an issue. It's not the same thing for the transition parameters and for the detection parameters, where we get something. There's clearly the mixing is not that good, and the autocorrelation is probably an issue. And you can see that in the numerical results. And you see the effective sample size for survival. So we have 10,000 iterations. Huh? So for survival, it's quite good, and it's high. But you see that the effective sample size for transition probabilities and for detection are much lower than for survival probabilities. So it's really this issue of mixing that decreases the effective sample size. So we would have to run it for a bit longer to get a better precision in the approximation of the posterior distribution, right? Okay. Any does the code make sense in the exercise? Can you make sense of the code? Do you have any questions, or go ahead? Huh? Feel free to ask anything that comes to your mind. Yeah. Oh, there's something on the chat. Yes, code is clear. Okay. So in my experience, really the thing, well, it's really the model building that takes time, and and it's really building those matrices here. Maybe Michael or Marc can comment on that, but this is where you build your model. This is where you have your ecological assumptions you want to test, and so this is where it takes time. And specifying the priors, because as we will see, it gets a bit more involved if you have more than 2 states or more than 2 sites, three, excluding the dead site. Is not very close to 1. No, indeed. You mean this one? In exercise 3. Did I? In the code you run, you mean? When you run the code, the R hat. Yeah. Okay. Yeah. Yeah. So it's a case where when the R hat is not really good, you really have to you have to increase the number of iterations. On the other hand, when the R hat is close to 1, it doesn't necessarily mean that everything is going well. So you should always check the chains, right? So it works. It doesn't work both ways. It's it's a necessary condition, but not sufficient, or the other way around. So always check the chains with the trace plot functions, for example. So I can run it just to make sure that I get something that makes sense. The recording, the data, the inits. It's very few iterations, and it's yeah, 2,100 iterations, 2,500 iterations, and only 500 iterations is burning. So we would definitely need to run that for longer. It was just for the demonstration to make sure that it wouldn't run for. Okay. Well, yeah. Yeah, you have 3 chains, and the thinning is quite long, which means that yeah. Anyway, we can run that. But it's also, I mean, it's multi-state model, so you get. Hang on. Up. No. Yeah. So it's okay, but it's not. It hasn't converged yet. Yeah. You can default that. Okay, so the easy one, Amélie, it's the standard deviation of the random effect, of the temporal random effect. And for Madden, whoa, that's the initial values. You get that in when you def. Amélie, did I answer your question? Yeah.
Yes, thank you.
Okay. Madden. Is it when you run the Jags that you get this error?
Yes,
I think it comes. Yeah, yes. I think it comes from this here. That if you do that, just to check to locate the issue. If you do that, just that, so you generate initial values for the latent states. Do you get the same error?
So, Olivier, I don't understand what you mean there. So it's run that line of code in 273.
This one in the console, if you just pick, you see my
yes, I see
my
that
pointer here. If you just copy paste that in your console here, does it produce something, or do you get the same error message you had?
No, it has a long list of stuff.
So it's working. Oh, it's working. Oh shit. Okay. I don't know. I would. Okay. Can we have a look to that during the break? Do you mind?
Say it again.
So that we can we have a look to that during the break?
Oh yeah, sure.
So because I was planning to resume the lecture, and yeah, so we can have a look together. You can share your screen and we'll have a look. I think it's I think to remember the issue. Maybe can you do everything again from the beginning? Like copy paste the data, read in the data, and then go through first the calculation of the first detection and so on, and the recoding here. Recoding here.
I don't get any error anywhere else until
you run the Jags. That's it.
Right.
Yeah. Okay. So we'll have a look together. I think yeah, it shouldn't be too difficult to pinpoint the issue. Okay. Questions on the code? You get the temporal random effect. Everything else is what we saw in the lecture. The only thing that's new is those transition parameters, and also that we have now we have 2 survival probabilities. And oops, I'm gonna increase the font size so that you can see. Yeah, and you can see here that for survival A, we don't use a link function because we have those alphas here. Or they could be, I mean, you could do that directly. Yeah? I could do that directly, actually. Okay. I have this extra step where I define the alphas, but well, I don't need the alphas actually. It's directly the survival between t and t+1. So I say, okay, they have a prior uniform prior, so I don't need a logit link to make sure that the survival are between 0 and 1. The prior is doing the job for me, okay? Whereas for survival in B, this is a bit more involved because I have this temporal random effect, and like Leo said before, the mu plus epsilon can make the survival being less than 0 or larger than 1. So I need to constrain the survival, and to do that, I use the logit, so that logit of survival in B is between -infinity and +infinity. So this can be a negative or larger than 1, it's no problem. And then I back transform to get survival in B between 0 and 1. Okay. Okay. Right. Back to the lecture. Where's the lecture? It's here. Okay. Exercise 3 is over. So I'm gonna spend a few minutes on several examples of multi-state models, just to kind of demonstrate or illustrate that multi-state models are very flexible. And if you haven't done it yet, I encourage you to read this other paper by Jean-Dominique Le Breton, which was published in 2009, where Jean-Dominique and several other co-authors, including Richard Barker, Jim Nichols, and I can't remember. Roger Pradel was in there, I think. Anyway, they go through a bunch of models that actually can be formulated as multi-state models. So it's kind of the mother of all models, multi-state models, if you prefer. Okay, so let's go through a few examples. First, well, we said multi-state models are a generalization of the Cormack-Jolly-Seber models, but I haven't actually showed you in what sense it's a generalization. I just said, okay, we go from alive and dead to alive inside A, alive inside B, and dead, and this is a generalization. But actually, if this is an actual generalization, you should be able to fit a Cormack-Jolly-Seber model from what we've just seen, the code we've just used, and this is what we're going to do here. So we need two states. So sometimes you will hear single state model for Cormack-Jolly-Seber model, but I just realized that it's not really it's an unfortunate formula, like denomination. It's not a single state. You have two states, and that's the force of these models. You have alive and dead. Okay, so that's how you can model a survival and the fact that you don't survive, you die. Okay, so two states, alive and dead, and then we need the transition. The transition matrix. So for the transition matrix, remember you have the states in rows and the states in columns, which are the same states, but at time t+1, the next occasion. And the two states we need for a Cormack-Jolly-Seber model are alive and dead. And then you have alive at t+1 or dead at t+1. And the probabilities of being alive or dead at t+1, given that you were alive at t, is just survival and mortality. Okay. And if you're dead at t, the probability of being alive at t+1 is 0, and 1 of being dead. You remain dead if you're dead at t, okay? So that's your transition matrix. It's a 2x2 matrix, easy. And your observation matrix, again, you have the state in rows at time t, and you have the observations at time t at the same occasion in columns. So you have seen and not seen. And so the probability of being detected, given that you're alive, it's the detection probability by definition. That's the definition of the detection probability. And the probability of being missed or not seen is 1 minus p, given that you were alive. And if you're dead, well, you're not seen for sure. So with probability 1. Okay. So it's really the formulation of the Cormack-Jolly-Seber model in the multi-state framework with the transition and the observation matrix. The transition is just, well, there is no longer any transition from from site A to site B. It's just one state, one alive state here, right? And you can actually use exactly the same code we used in the exercise 3 or in the lecture, on the multistate lecture, and to fit a Cormack-Jolly-Seber model. You just have to change the transition and the observation matrix. You don't have to make any change in the likelihood. Huh? It's general enough to be able to fit simpler models, including the Cormack-Jolly-Seber model. So you take the transition matrix. Now it's just 2 states at t and 2 states at t+1. We keep the second and third dimension for individual and time, and we constrain those parameters to be just survival, time-dependent survival, or 1 minus survival t. So it's exactly this 2x2 matrix here that we write down here, PS or PO, the big theta. You remember in the lecture before. Again, it's a 2x2 matrix where you have the state at t in rows and the observations at t also at the same occasion in columns, yeah, with p and 1 minus p. I have some code on GitHub. On GitHub, if you want to convince yourself that it's working. So I think I use the deeper data or some simulated data, and you get exactly the same results as if you were using the formulation we saw this morning with just 2 Bernoulli distributions, right? Okay, let's have a look to more interesting examples and examples that really justify the use of multistate models. So we saw examples with sites, geographic locations, and dispersal between those locations. But as I said, we can have instead of sites, we can have states, and for example, breeding states, like breeding states, and the fact that you're non-breeding, so for birds or whatever, and at time t. You are either breeding, non-breeding, or dead. And then at t+1, you might be breeding if you are breeding at the previous occasion with some probability, which is given by, well, it's the product of survival of breeder and breeding individuals, or breeders, okay, times the probability of remaining, of staying breeder individuals, okay, breeding individuals. Or if you were a breeder at time t, then you go to the non-breeding state with this probability here, the survival, and you survive, you stay in the alive state, but you go to the non-breeder state with probability, the transition probability from breeder to non-breeder, okay? And you may die, of course, with the probability 1 minus the survival probability. And the sum of these 3 probabilities on this row here is 1. And same thing, well, same thing, not same thing, but same reasoning. If you were non-breeding at time t, then you have some probabilities to move to the state breeding at time t+1, staying in the same state, or dying. And if you're dead, well, you remain dead with probability 1. And for the observation process, well, it's we just the cool thing is that now we can have some have heterogeneity in the detection process due to the breeding state. Okay, so breeder individuals might be more capturable than non-breeder individuals, right? Okay, so we can test that. Actually, we can have a model where we distinguish the 2 detection. We make those 2 detection probabilities different, and another model where we say, okay, this is the same detection probabilities, and then use AIC or WAIC or DIC to compare the 2 models, right? And for here, so that's one assumption you might be interested in testing, but another assumption, which is probably much more interesting, if you're interested in life history trade-offs, like survival and reproduction trade-offs, you might want to test a model where the survival of breeder individuals and non-breeder individuals is different from one another. So and test whether the survival of breeder individuals is lower than the survival of non-breeder individuals. Okay, so you might want to compare this model with a model where the survival between breeder and non-breeder individuals is the same. So you have one single parameter for the survival. and see whether this model is better than the model where you distinguish two probabilities. So that's what I was saying this morning. By splitting this the survival and the transition processes, the two processes that we are interested in, then you can test assumptions and effects that are different on the survival and on the transition probabilities, right? Okay. Up to, well, so far what we've used is only two alive states, A or B, and the dead state, so 3 states, but the alive states were just, there were just 2 alive states. Obviously, it's not that obvious. We can extend that to more than 2 alive states, for example, three sites. And you might want to be interested, you might want to investigate, I don't know, dispersal between among those 3 sites. And actually the original paper on multistate on multi-site models was about dispersal between wintering areas for the Canada geese, and that's exactly the kind of model they were fitting in another framework, but that's the same idea. Okay. And you might want to have covariates to test whether the dispersal from one side to the other is I don't know, related to the distance between the sites, for example, or stuff like that, right? So you see where I'm going. Once you've set up the model, then you can test some assumptions like in the GLM-like framework that Marc presented yesterday. And then the observation process, well, you may have a detection probability that is site-specific, but you can also test whether the detection is the same for the 3 sites and so on. So it's, yeah, the combinations starts to become not infinite, but numerous. Okay, the only difficulty in a model where you have more than 2 alive states, so at least 3 states, including the dead states, is that the tricky thing is that the transition parameters, they have to sum to 1. It's being in a site, these are mutually exclusive events. You cannot be in 2 sites at the same time. So when you sum all those parameters, moving from A to B, from A to C, or staying on A, the transition parameters, the sum of these 3 transition parameters has to be 1. Okay, and that's a different link function. So it's a kind of an extension of the logit function. So you have to have the transition parameters to be between 0 and 1, like before. It's a probability, but also the sum has to be 1. Okay. To achieve that, you have 2 options. The first option is to use a multinomial logit link function, which ensures that each transition probability is between 0 and 1, and that the sum is 1. So that's one way to do it. And I give you several references to check out. And you can also use the Dirichlet or Dirichlet, I never know how to pronounce it, Dirichlet prior. And there is a nice example, and Marc talked about that yesterday, and there is an example in their book in chapter 10. Okay. Another example with breeding states, something a bit more involved, where you're interested in estimating the accession to reproduction. And then in that example, the key questions we might want to ask is, for example, when do the individuals start to reproduce, or what is the mean age at first reproduction? And the model we would use to do that is, for example, similar to that one, where we assume that at age 3, everybody starts to reproduce. Everybody reproduces, but there is some delay in the accession to reproduction, in that sense that, for example, okay, the states first. So we have juvenile state, we have 1 year non-breeder, 2 year non-breeder, breeder, and dead. Okay, and same states here for the transition matrix, but at time t+1. And for example, if you are juvenile at time t, you become 1 year non-breeder. So you don't breed, but you have 1 more year, and you survive with some survival, but you don't reproduce. And so there is a fraction of these juveniles at time t that won't reproduce, and the complementary fraction, alpha 1, which will reproduce, okay? So it's not full reproduction at age 1, but some of them will produce. And same thing for the 1-year non-breeder individuals. They survive with some probability. Some of them will reproduce with alpha 2 probability, and some of them will not. And then from age 3, so 2-year-old non-breeder individuals, all individuals will reproduce, and they would just survive with some probability. And then when you're a breeder, you survive with another probability. So yeah, by doing that, imagine that you increase the number of age classes. You can actually test. You can actually compute the age at which you start to reproduce, and you can test using AIC or WAIC, or we're in Bayesian framework, WAIC or DIC. You can test at what's the best age structure, and it will give you the time at which you start to reproduce. There is a very nice paper by Roger Pradel on flamingos about that, where they start they test several structure on the age of first reproduction, and then they test several models, and they get the optimal age of reproduction. It's a very nice paper. Okay. And then the observation process, that's the same. It's a standard matrix. Okay, so temporary migration, that's one assumption we had a look at that, or we mentioned that, saying the fidelity and so on. So here it's a model where you can actually estimate the probability of temporarily leaving the study area. And to do that, that's actually a model that Michael developed back in 2004, if I'm not mistaken. Sorry, 2004. Okay, that's a long time ago. Okay. Anyway, and so you have at time t, well, the 3 states we consider is being alive and inside the study area, or being alive and outside the study area. And you might ask, well, outside, but if you're outside, how can you really observe individuals? Stick with me for a second, and you will understand that. And the state dead, and then at time t+1, you have the same 3 states, okay, inside, outside, and dead. And then you can write down the probability that you are inside, given that you were inside at time t, and you are outside. So these are the probability of leaving or remaining in the study area. And the trick is to have these, the trick is in the observation matrix, where if you are in state inside the study area, then you can be observed or non-observed with probability P. But if you are outside, for sure you will be missed. So this state is actually unobservable. So in the literature, in the capture-recapture literature, this state is, these models are called unobservable. This state, this outside state is called an unobservable state. And with this kind of model, you run into identifiability issues like we saw this morning, and you have to apply a few constraints, like to make it identifiable. If you're interested in this kind of models, check out Michael's paper from 2004. Another model is a model with a trap effect, whereby you have your detection process is affected by the way you capture individuals in a positive fashion or negative fashion. If you use bait to attract to capture your individuals, well, you may get a detection probability at the next occasion that is higher than before, because you have used a reward for the animals. But it could be the other way around, where the capture is traumatizing for individuals because it's physical capture, or you do something funky when you capture the individuals, and then the recapture probability will be lower if you've been captured before than if you haven't been captured before. So you can account for that in the detection process, and it's important because it can lead to a huge bias in the survival probability if you don't account for that. So to do that, you define 3 states: alive and seen. So you see, I'm not really a big fan of this formulation, but you'll see why. It mixes kind of the states and the observations. Okay, so it will work, but it's okay. It's a quick and dirty way to account for trap response, trap effect in capture-recapture model. But anyway, so you define alive and seen, alive and not seen, and dead, and the state at t+1 are the same. And the trick is that the probability of being alive and seen at t+1 is gonna depend, or it's gonna be different depending on whether you were seen or not at the previous time occasion. Okay, if you were seen at time t, then the probability that you are still alive and seen is going to be the survival probability and the detection given that you were seen before. And if you were not seen before, it's going to be the product with times the detection of individuals that were not seen before. Okay, so the trick is that you distinguish the detection probability according to whether you were seen or not before. So it's kind of a mixing the state process, the survival, and the observation process with the detection here. But the thing you need to remember is that by doing that, you distinguish the 2 detection probabilities according to whether you were captured or not the occasion before. And this is how you deal with immediate, meaning the first order, trap response. Okay, and so it might be that the probability of detection for individuals that were seen before is higher because you use a reward on the individuals to capture them, or lower compared to whether you were not seen before because the capture is was traumatizing for individuals, for example. Okay. And for the observation matrix, there is nothing here happening because the detection process is already in there in the state process. It's kind of disturbing, but you see. So if you're alive and seen, the probability that you are seen is 1 because it's already in the state. And if you're alive and not seen, well, the probability is 1 for sure of not being detected. And if you're dead, of course, like usual, it's 1. So I think Roger Pradel has another paper, a recent paper with Arnason-Schwarz in +1, where they kind of well, we formulate that in a more elegant way. Anyway, okay, a combination of live and dead encounters. So it's not live, it's live and dead encounters. So it happens when you have for example, you're studying game species where the birds, for example, are shot, and so you get recoveries, but you also get while they're still alive, you can get recaptures of those individuals, and you want to combine these 2 pieces of information. So that's kind of it's echoing what a question I had this morning about you have 2 observation processes. Here it's the recapture of living of alive individuals and the recovery of dead individuals. And so how do we do that? As I said this morning, in terms of the state process, the ecological process, the survival process, it's the same whether you're alive or dead. I mean, you just alive or you just died, and then you died for good. That's a trick. Anyway, we can go further with that. But what you just have to focus on is you have a state alive and a state dead. And if you're alive, the probability that you're still alive at the next occasion is the survival probability should be a 5 here. But well, and it's a kind of a true survivor. And then you might be recovered dead through the recoveries after you've been shot by a hunter or whatever, and then it's the probability of dying on this time interval. Okay, and if you just died in the time interval, then for sure you will go into this what we call an absorbing state, a dead state for good. Okay, And then if you're dead for good at the following occasion, then you remain dead. And this is where things get interesting, is that in the sense that you have the two observation processes that occur here. It's that if you're alive, the probability of being detected or seen or recaptured is the probability of detection, like we saw before in the Cormack-Jolly-Seber model, or not seen with minus p. And then the probability of being seen as dead, recovered as dead, recovered dead. Sorry, it's another observation process that involves other processes than when you capture live individuals, and this is this parameter little r here, which is the recovery probability. Okay, so this is where the two observation processes occur: the p for the detection of alive individuals, and little r for the probability of recovering dead individuals. We can actually achieve even more flexibility with multi-state models or generalization of multi-state models, but I lost track of time. When are we supposed to do another break? It's a bit early, no? Michael, did you keep track of the time or not?
Not really, but sorry. But
I don't know. I know it's 25. No, I still have time. Yeah. I started 25 minutes ago, so we still have time.
Okay.
Okay, so we're gonna go for something even more flexible than multi-state models. These are called multi-event capture-recapture models. So what are these models? Oh, there are several questions in the chat. Do you I can't really let me. No, I cannot access the chat. Okay, I trust that Michael and Marc are answering your questions. Okay, multi-event models. These models extend multi-state models in the sense that they allow you to account for uncertainty in the assignment of a state. We saw the state alive in A, B. So you have some uncertainty in the state, and you don't know how to assign a state to an individual. And this happens all the time in real life, huh? And we're going to see a few examples. But so you see that when I say that, I'm going a step further away from multi-state capture-recapture models, in the sense that the assignment of a state can be uncertain. So it's a generalization, and if the assignment of the state is certain, then you're back to multi-state models. Okay, examples. For example, let's say you monitor female roe deer in the field, and you're interested in knowing the breeding status of female roe deer. But you assess the breeding status of roe deer or female roe deer by checking whether the female is suited by with a phone, and if you don't see the phone, it doesn't necessarily mean that the female is non-breeding. It's just that maybe you might have missed the phone. Okay, so if you see a phone, for sure the female roe deer is in breeding status. But if you don't see the phone, it might be that you missed it, and it's actually a breeding female, but you don't know whether you should assign it to the breeding state or the non-breeding state. Okay. Another example is when you want to ascertain the sex of an individual based on morphological criteria. So I took the liberty to really focus on one species, because I give a corresponding paper where they used multi-event models, and you can check out the paper. It's in the directory papers in the Dropbox for today, for Wednesday. And you'll see that they're using multi-event models to fit these to fit this data, to fit their models to this data, to this kind of data. And so you use I don't know, the size of the individual to assign the sex, and sometimes well, you have some uncertainty and you don't know whether it's a male or a female. And so it's this kind of models are really useful in that case. You can really make explicit the the way you assign a state to an individual, and so you can account for uncertainty in this assignment. It may happen in disease ecology when you try and estimate infection rate or recovery rate. For example, in this paper by Kohn and Kuch, they studied house finches, and it was conjunctivitis. I always forget how to pronounce that, but you know this disease, and what they did to ascertain the disease status, is that they have to capture individuals and check the eye of the bird to know whether it has conjunctivitis or not. I think I'm missing a seal level, but I'm not sure. Anyway, okay, so in that case, the tricky part is when you see an individual, but you cannot capture it physically, so you cannot do the examination, and so you don't know whether it was sick or not. You know that it's alive, but you cannot assign a disease status to that particular individual. Okay, you see it, but you cannot capture it physically, and you cannot know whether it was sick or not. Another example. So there are many examples in the literature. These models are really awesome. A bit more involved to fit, but awesome than multistate models. Okay, in wolves, for example, Nina Santostasi did this study very recently, where she was interested in hybridization between wolves and dogs, and we kind of assigned a species to an individual using genetics, and genetics is all about thresholds, and well, sometimes this threshold is kind of blurry. We don't really know where to say where to put the threshold to say it's a wolf or a dog, and we tried and accounted and try and account for this uncertainty in this study here. And another example, and I think it will be my last example, in this paper by Sarah Kubain. Still in wolves, we love large carnivores. We had well, it's a social species where dominant status is very important to, and it has an effect on demography, the way that, I mean, if you are dominant or not. And the dominant status in wolves in this particular population in France, we kind of tried to assess it based on heterogeneity in detection, and the fact that individuals that are highly capturable are dominant, and the other ones are kind of non-dominant. And there was some uncertainty in how to assign individual in the lowly capturable class or the highly capturable class. Okay, several examples to show you that it's not as simple as multi-state models, in the sense that we cannot assign a state to an individual with certainty, and you have to explicitly consider the way you assign a state to an individual in the model. So we're going to need extra parameters to say, okay, I can assign this state to that individual with some certainty, given that the individual was in that state, is in that state. Okay. So in a sense, all capture-recapture models can be seen as special cases of multi-event models. So the same spirit. So you have a very general formulation, and all the other models can be deduced or obtained from this very general model by using some constraints. So the seminal paper, the landmark paper, is by Roger Pradel in 2005, and we also had a paper in 2012 in which we did some kind of review of multi-event models and model with a hidden structure. And to be fair, actually, the idea was already in the air with Jérôme Dupuis from the University of Toulouse, who published this paper in Biometrica in '95. He had a very similar idea to that of Roger, who published in 2005. Interestingly, it was Jérôme published a paper in the Bayesian framework. It was for the Arnason-Schwarz model only. And Roger really took the idea broader and extended it to many cases. Okay, so how does it work? Same schematic as before. So we have an individual with this fate here. Now you should be used to that. we have an individual with okay, at first occasion, it's in state 1, and then state 2 remains in state 2, then goes back to state 1, stays in state 1, and then dies, and then remains dead. Okay. And then, so that was the state process, and the observation process. The model is still conditional on first capture, okay, when the individual is first captured, but the state at first capture might be difficult to record. Okay, there is some uncertainty, so it's no longer deterministic, the link here, but there's going to be some distribution to say, okay, it might be at first capture. Okay, you're alive for sure, but you might be in state 1 or state 2. We don't really know. Okay. And then same thing for the other occasions. So there are two kinds of uncertainty. First, an individual may or may not be recaptured, and second, given the recapture, its state may or may not be assigned to that individual. Okay, so these are the two sources of uncertainty now. It's no longer only the detection process that is the main source of uncertainty, but you also have the state assignment that generates some uncertainty. Okay. Okay. So an example. Let's spend some time on an example to fix ideas. Uncertainty in breeding status. So I give you. There's several papers that it's just a few examples, but I love those ones. You have 3 states, so it can be I don't know, female rodie, it can be kittiwakes, it can be, in that case it was bottlenose dolphins, any species in which you have some uncertainty to kind of assign a breeding status to the individual. So you have 3 states you're interested in. Okay, so it's the data you wish you had. Again, breeding, non-breeding, and dead, right? But on the field, you can only observe 4 things. You don't have access to the truth, especially when you're not found, when you're not encountered. So you're going to code that 0, but we're going to code it 4 later on, but let's say it's non-detected for 0. And then 3 other detections or observations, sorry. You found, you're detected, and you're assigned, you're classified as a breeder, okay? You're detected and you're classified as a non-breeder individual, or you are found, but we don't really know how to assign you a status. Your status is unknown. Okay, so it's really the same thing as in the disease ecology example, where for the house finch, when an individual was not captured, but we knew that it was alive, we couldn't assign a status. Okay, so in the example, it's a female warrior where you saw it. You detected the female, but you cannot assign a breeding state because the fauna are not seen. But it doesn't mean that that it's not a breeding individual. Okay. So what are the possibilities? In other words, how do we build the model? Well, we start with states, so the 3 states here, and we have the observations. And if you are a breeding individual at time t, at the same occasion, the 4 observations that are possible, the 4 observations are possible. If you are a breeder individual, you could be non-encountered, found, identified as a breeder. Oh, sorry, and of course you cannot be found and identified as a non-breeder because you are alive and breeding. Okay, or you could be found and your status could not be assigned or ascertained. Okay, assessed. It's the case of the female warrior with which you see without a phone. Okay. Now, if you are a non-breeder individual, again, you can have the 3 possibilities: not encountered, found and assigned to the state breeder, or found and you don't know the status. And if you're dead, the only option, the only observation, and it's deterministic this time, it's that you are not encountered. You cannot be found anymore. And each alive state can generate 3 different observations, okay? Either non-encountered or found in the state and in the corresponding state, or status unknown. So how do we build this model? And this is let's specify the model. First thing we need and it's a big difference with multi-state models, we need initial state probabilities because we cannot assign states to individuals with certainty, even at the first encounter, okay? So we're going to define pi b, the probability that a newly encountered individual is a breeding individual, is a breeder in that particular example where we're interested in breeding states. And we write down that the probability for each state at first encounter, breeding, non-breeding, and dead, and we write down those probabilities, and we put them in a vector of initial state probabilities. Okay, so at first encounter, either you are a breeder with probability pi b, or you are a non-breeder with probability 1 minus pi b, and you cannot be dead. Okay, because you are detected. It's just that we don't know where to put you. Okay. And in Jags, well, we're going to use again. It's not a Bernoulli because actually it could be a Bernoulli because it's not a binary event, a binary random variable where you just have alive or dead. It's alive and in state breeder, alive and in state non-breeder, or dead. Okay, but in that case, because you're dead for sure, at initial encounter, you could use a binary distribution, but we're going to use a categorical distribution for homogeneity with the rest of the model. Now for the transition parameters, it's not there that anything happens because it's really the uncertainty is in the state assignment. So it's in the observation process in a way, okay? So the transition parameters, the fact that you survive or die or you move or you stay in the same state, it's not affected by, why it's not affected. The way you build the model is not affected by that. And obviously the estimation of those parameters are going to be affected, but the way you build the transition matrix is the same as in the multi-state models. So we saw that already. We're going to use a categorical distribution for the latent state. You're alive and breeder, alive and non-breeder, or dead. Okay, the Z. Now the observation parameters. The main difference between multi-state and multi-event models is probably here in the observation parameters. Okay, we introduced two new parameters. We have delta B, which is the probability to assign individual in state B, an individual that is alive in state B to state B. Okay, and delta NB for non-breeder, the probability to assign an individual in state non-breeder to the state non-breeder. Okay, so it's the probability of correctly assigning a breeder individual and the probability of correctly assigning a non-breeder individual. Okay, and then the observation matrix is that one. So we have, it's like before, we have the states in rows, so breeder, non-breeder, and dead, and then we have the observation in columns. Okay, so the observation are you detect, you're found and assigned to the breeder state, you're found and assigned to the non-breeder state, you found and you cannot be assigned a state, so it's 3. And then the non-detection, it was 0 before, but we, like in Jags, we recoded it because Jags doesn't like indexing starting at 0. It's not C++, and so we have to recode it to 4. And we say when you're non-detected, you're gonna get the value 4 for Y for the observation. And so it makes perfect sense because, for example, so again, in rows, the states, observations in columns. For example, let's say this one, the probability of being detected and assigned to the state B. So it's 1 here, okay? Given that you are in state, you are alive in state B, it's the product of the probability of being detected and assigned to the state B, okay? Whereas the probability of being detected and with a status unknown, the 3 here, given that you're alive and in state B, it's the probability of being detected in state, the probability of being detected for breeder individuals, because you're alive as a breeder, okay, times the probability of not being assigned in the breeder state, right? And so on. So this matrix here, it's really a combination of the detection process and the state assignment process. And so we will use a categorical distribution, and Well, the observation matrix is a bit different from before in the multi-state case because we have those delta parameters. Okay, in the multi-state case, delta here is equal to 1, and you don't have this column here. You don't have this column with a unknown status. Okay, detected with unknown status. We don't have any uncertainty in the data, so we just have the first two columns and the non-detected column here, and the delta are equal to 1. So it's useful to split that in two and to say, okay, the first process in 2 steps, sorry, the first process in the observation matrix, it's the encounter. So you have the states, you are encountered as a breeder individual, you are encountered as a non-breeder individual, or you're not encountered. So here in this matrix, we have only the detection probabilities, okay? So I kind of split this matrix here in a matrix product where I have 2 terms. The first term is for the encounter process, the fact that you really capture or detect the individuals. And the other step is for in that particular case, the breeding assessment. The fact that once you're detected, you will be assigned to a state breeder or non-breeder individual. So if you're encountered, then you'll be assigned to the breeder state with probability delta B. You cannot be assigned to the breeder state because you're non-breeder state because you're a breeder, or you're not assigned in that state. You cannot be assigned, okay? But we know that you are a breeder individual, and so on. So it can be useful to split that in two because you can really understand better, maybe, or maybe you prefer that one. I just give you the two presentations, the two formulations, the 2 parameterizations, and you pick the one you prefer. The last thing I want to go through is that this observation matrix here, when we are at the initial state, there is something we need to take care of, is that when the encounter is a bit, it's degenerated in the sense that when you are at initial state, all animals are captured. Okay, that's the first encounter of any individual. You all captured. So the detection probability is 1, whatever your state. So this matrix, the first encounter matrix here in the formulation in 2 steps, all the p's are equal to 1, right? But at step 2, the breeding assessment, it's not affected by the fact that you are at first encounter. Okay, the initial encounter. You still have to have this the assignment to one state or the other, right? So at first encounter, the detection is 1, but the assignment is still to be estimated. Okay, so to sum up, for the multi-event models, we need 3 things. We need the probability of observations, conditional and current state. So it's the same thing as in multi-state model, but we have uncertainty in there. Okay, so that's for the link between the observations and the state. You also need the initial state probabilities, so that's a bit new. Okay, this wasn't the case for multi-state models or the Cormack-Jolly-Seber model because we had a deterministic relationship between the observation and the states at first encounter. It was known for sure. Here we have some uncertainty, and then we have the probability of transition that make the link between the state at one occasion and the state at the next occasion. Survival or survival times some transition process. These models are really these models are what we call hidden Markov models. Basically, they are Markov models, but with a hidden layer. That's caused by the detection process, where when you don't detect an individual, you cannot really assess the state of the individual. So these are called hidden Markov models, and actually these models are just that's what we call them state space models yesterday, for example. But in the case of capture-recapture model, we have discrete states. If you remember what we've been working on since this morning, it's just discrete states: alive or dead, alive in site A, alive breeder or whatever. It's always discrete states, and the structure, the dynamic of the states, the way you go through occasion t to occasion t+1 is always Markovian. So the state at next occasion is dependent only on the current state, okay, and not on the past states. So it's really a Markovian structure with discrete states. So state space model with discrete states and Markovian structure are what we call hidden Markov models. And well, we have this, we actually, Brett and Roland worked a lot on this paper that we just published, where we really review the use of hidden Markov models in ecology. And why do I spend the time talking to you about hidden Markov models? Because, well, that's a very promising kind of a unifying modeling framework, especially for integrated population models, and in particular Panayotis, Takis, and Byron Morgan published recently this paper in Biometrics, where they kind of formulate integrated population models in the hidden Markov modeling framework. So that's really promising. Okay, and I think I have one last slide, and we will have a break. I think, yeah, we will have a break. It's something I wanted to talk about just briefly. It's we already have kind of seen that in the exercise. It's that capture-recapture models, and especially multistate, and you see that multi-event models is even worse. They can be very slow. And I wanted to share a few tricks with you to speed up the computations and maybe improve convergence. So that's something that's kind of an open discussion, and Marc, Michael, and anyone, you feel free to jump in the discussion. So the first thing, that's something we've seen in the exercise. So what we wanted to show you is something kind of a general structure, and then you apply linear constraints and you get simpler models. But in practice, if in your analysis you're just interested in constant parameters or just time effect, I mean temporal variation, then you don't need to have the individual dimension, and so you can simplify and maybe get rid of the loop concerning when you define the transition observation matrix. You can get rid of the unnecessary loop. You can get rid of the loop on individual and save some memory, and it will go faster. I mean the fitting process will be much faster. So that's one thing. Don't forget about that. The other thing is to so we talked a lot about latent state, the Z, the fact that you're alive or dead, or alive, okay, not the observation but the states. But actually, if you remember, we can in the Bayesian framework with the MCMC algorithm, we can estimate the latent state. There are just other parameters in the Bayesian framework that are treated as a parameter, as a survival or a transition parameter. But you feel that they don't have the same status. It's latent state, and it's the fact it's a random variable, but they are treated like parameters. Okay, that's the Bayesian framework, so it makes sense. But actually, we haven't really tried to estimate those parameters. So it may be that actually we don't need these parameters in some examples, or in some studies, some analysis you're doing. And there are some ways to get rid of the latent states and do what we call marginalization. So you condition on the latent state and you get rid of them. And by doing that, actually, you get rid of a lot of dimensions in the model, a lot of parameters not to be estimated, the Z, the latent states, and it makes your life much easier when it comes to fitting models in a reasonable amount of time. So it's really in the case where you don't need the latent states. If you need to estimate the latent states, then you have to go through what we've seen this morning and this afternoon. Another thing I haven't had time to show you is to use, rather than sticking to the like the individual based format of the data. So each row in my data set is individual. There is a way to kind of make the formulation denser, to have something of lower dimensions. And this is what we call sufficient statistics. So it's kind of a summary of the data. So you're no longer having the capture-recapture data displayed as occasions in columns and individuals in rows, but you have something that is very, very, very much much more condensed, but you still have the same amount of information to estimate your parameters. Okay, so that's the trick. For some models, you're able to build sufficient statistics that summarize all the information you need to estimate, for example, time-dependent survival or time-dependent detection probabilities. It won't work for all models, like random effects or stuff like that, but it will work for some of them. And so we have a few slides on that in the bonus slides. So there is, if you go a bit further in the lectures, we have bonus slides, so you can have a look. And also, well, in Michael and Marc's book, you have that also. And there is this paper by Ruth King and Rachel McCree, where they go through parameterization of the Arnason-Schwarz model with MRAs with sufficient statistics. And last thing is okay, we used the Jags to fit our models in the Bayesian framework. It might be that the MCMC algorithms that are used by Jags for a specific problem are not really well suited. And in that case, it might be a good idea to switch to other software, other pieces of software. So we mentioned Stan, and I agree with Marc. For now, it's not might not be a good idea to switch to Stan to fit capture-recapture models or occupancy models, but I'm still open to it. I haven't made the step to switch to Stan yet, but we'll see. But Nimble is the new kid on the block, and it's very, very efficient. It allows you to take full control of the MCMC machinery, so you have a bunch of algorithms that you can pick and use, not necessarily the ones by default. You can also code your own algorithms, and it's very efficient. And you will have an example by Mod on Friday of a big multi-event model where the switching to Nimble was really the good idea to speed up the computation, to reduce the computational burden. And the other thing is if you want to get to reach better convergence, you might want to use maybe more informative priors or pick better initial values. That one is really good advice. Not from me. It's something that have been advised by several people. So pick better initial values for the algorithm. One trick, one thing to be able to propose clever initial values. Sometimes it's to start with a simpler model. I mean, you after a very, you have a clear model in mind, but rather than starting with this complex model, you start with something much simpler, and you use the parameters you've estimated from this simpler model as initial values for the complex model. And it will help. It will help a lot because it will help the algorithm to converge faster to the right stationary distribution. To the stationary distribution, there is only stationary distribution, and that's all, I think. Yeah. Okay. So my suggestion is we take a break for 15 minutes until 4:30, and then I have an exercise. So the exercise can take I don't know, 15 minutes or half an hour. It's up to you. I can stay until 5, I think. And it's an exercise on how to fit a multi-event model. So it's really very general. Okay. So do you say we take a break until 4:30, and then we take 15 minutes or half an hour to do the fourth exercise? Okay.
Okay.